So in this lecture we'll try to build an op-amp or try to build a voltage control voltage source using an op-amp, okay, with k greater than 1, which means I'm going to build an op-amp with Vout is equal to some k times Vin. Okay, so this is what I'm going to do. So here Vout by Vin will be k. So the first step is to figure out the equation, right? So the equation is Vout is equal to k times Vin, and I know that I have to compare the two quantities, and as we discussed earlier, k times Vin is what I want eventually. So it's not, I don't have a reference quantity of k times Vin as such, but it's always desirable for me to come up with a quantity of Vout by k. Okay, so I would rewrite this as Vout by k is equal to Vin, which implies Vin minus Vout by k is equal to 0. So this is what I should use. So I have to compare Vin at one terminal and Vout by k at another terminal. See, so as I said earlier in the last class, you have you have an op-amp which is a voltage controlled voltage source, and the equivalent circuit of an op-amp is something like this. This is the positive terminal, this is a negative terminal, and the difference between these two terminals is Vd, and you have a voltage control voltage source, because op-amp in itself is a voltage control voltage source. Okay, voltage control voltage source using op-amp. That is what we are trying to do. And op-amp itself is a voltage control voltage source. So it will have some gain of A0 times Vd, and this A0 is very, very large, okay, and that's why we want to put things in feedback to achieve the gain of k. Okay, so this is the output node, or output terminal rather, and this is what I have. So how do I construct this is the question. So I know that if I can realize this case, then I could easily achieve what I want, and this can be done pretty easily. So one of the terminals should be Vin, the other one should be Vout by k. So out of these two, and it's obvious that if I put this as Vin and this as Vout by k, if the difference is, if suppose say for example, let me say that this is Vin and this is Vout by k. Okay, if I say like that, then Vd is equal to Vin minus Vout by k, right? Say if Vin is greater than Vout, that means my output voltage is reducing. Okay, so if this is the case, what I need is, I want, so essentially if Vin is greater than Vout, my Vd is actually increasing, but rather I want my Vout to increase so that my Vd will reduce. That is what I want. Okay, so this A0 times Vd is something that will also increase if Vd increases. So I have to feed the A0 times Vd. A0 times Vd is my output, Vout. So I have to feed it to the negative terminal, so that if Vout increases, this negative terminal will make sure that the difference will eventually decrease, right? For example, if you put Vout by k here and Vin here, then you cannot achieve the negative feedback. So the negative feedback is achieved when you put the output to the the output voltage here is Vout by k, and I want, if Vout is lesser than Vin, I want the difference to reduce. Okay, so eventually Vin is greater than Vout, so I see that my difference is increasing, and eventually I want my Vd to reduce. This is what I want. Okay, this is what I want, and I would achieve this when I feed back my output to the negative terminal in a way that any increase in the output would increase this particular node. If this node increases, the difference will come down because this is fixed. Okay, so that is the idea. And remember, it's not true that I connect the I connect the output voltage to the negative terminal and that is why it's a negative feedback. No, it's not like that. Sometimes there may be a case that you connect it to the positive terminal to have a negative feedback. Okay, so negative feedback is not determined by where you are it's not determined by connecting the feedback to the negative terminal. It is not at all like that. Okay, you have to analyze that. Okay, it so turns out that if you connect the output terminal to this part, so Vout by k will increase if there is a increase in the difference, that is by the virtue of the voltage control voltage source, and if difference increases, this node voltage increases, and you connect it to the negative terminal so that difference reduces, and then you try to maintain them in proper V in is equal to V out by K fashion. Okay, so let me construct it here. So this is what we have. This difference is Vd, and this is A0 times Vd, and this is the output node plus node minus node. So what you are doing is you are taking the output, which is V out, okay, and then you want to establish a feedback, and if you connect a resistor of value R here and K minus 1 R here, you will have a value of V out by K here, and then you take this V out by K and connect it to the negative terminal, while this terminal is given V in. Okay, this is what I said. If you do this, then you would establish this equation. Now let's go again, go through the calculation and see whether you are achieving what you want or not. Okay, so meaning the gain is equal to 1 by K or not. That is what I want to check, right? Because I have constructed the circuit in incremental domain. I want to check whether I am getting V out by K, V out by V in is equal to K or not. Okay, so let's do the V out by V in calculation. It's very simple. So let's put it down here. A0 times Vd is equal to V out, right? V out voltage at this point is nothing but A0 by A0 times Vd. Okay, at the same time we know Vd is equal to V in minus V out by K, right? So substitute it here. So A0 times V in minus V out by K is equal to V out, which implies V out by V in is equal to A0 by 1 plus A0 by K, and I can always rewrite it as K times A0 by K divided by 1 plus A0 by K, and if A0 tends to infinity, then we know that A0 by K tends to infinity, and I can neglect this 1 in that case, and this will get cancelled. So I'll get V out by V in to be approximately equal to K. This is what I want. Okay, and this concept of having A0 tending to infinity is called an ideal op amp. Okay, so if you take an ideal op amp, the first thing is you have A0 tending to infinity. The gain, A0 is the gain of the voltage control voltage source, right? And the gain tending to infinity, in reality it will not be infinity, but it will be very very large, that you can safely assume it to be infinity. Okay, so if A0 tends to infinity, we have seen from our lectures on negative feedback and op amp that your different voltage will tend to 0, right? So it's obvious to see from here also, if A0 is tending to infinity, it basically means that your different voltage, this particular difference voltage V in minus V out by K, right? So if A0 tends to infinity, V out is equal to K times V in. So V in will be equal to V out by K. In that case, your different voltage will tend to 0. Okay, so this particular concept, if difference voltage is tending to 0, which means what? This voltage and this voltage are the same. Although they are not shorted, they are virtually the same. So this concept is called virtual short. So this concept is called virtual short in op amp. In a case that you suppose have one voltage to be V in here, you can safely assume that this voltage is also V in, provided the op amp is in negative feedback. Okay, if you have an ideal op amp in negative feedback, then you can say that as long as A0 tends to infinity, your Vd tends to 0, and you can assume virtual short. And second thing is, look into the input side of an op amp, you see that my input impedance is infinity, right? That is what an ideal voltage control voltage source will have, and output impedance should go to 0. R out will be equal to 0. Okay, so this is what an ideal voltage control voltage source should have. So that is second property of an ideal op amp, and R out equal to 0. Okay, and why it is so? Because no current flows into the terminals of an op amp. Either you can derive that condition from here, or you can actually because input impedance is infinity, you cannot have any current flowing through the terminals of the op amp. Then only you can say that input impedance is infinity. So third one is no current flows into the terminals or rather to be specific, input terminals of the op-amp. Okay, so these are certain things that are very, very important. Virtual short is something that is very important, and then you have this condition of input resistance and output resistance, and because input impedance or input resistance is infinity, you won't have any current flowing into the input terminals of the op-amp. Okay, so given this case, you can always implement the same thing using op-amp as follows. For example, if I take an op-amp, let's assume it to be an ideal op-amp. Let's say it is an ideal op-amp. Okay, and I have an out node and I have the plus terminal and the minus terminal. Okay, and this is exactly same as having a situation, like a voltage control voltage source, where this is VD, this is plus and this is minus, and I have A0 times VD and this is out. Okay, so this is exactly same as this one, just that I have considered a model for an ideal. This is basically the model for the op-amp, which is a voltage control voltage source, and I have as far as it's an ideal op-amp, I need not go through this particular scenario of A0 being there and VD being there and all these things, because I know that this voltage and this voltage are the same. So as far as an ideal op-amp is considered, because A0 will tend to infinity, A0 will tend to infinity in an ideal op-amp. So I know that VD will tend to 0 in an ideal op-amp. So I will have a model something like this. So as long as you have an ideal op-amp, you can use a situation like this and proceed for your analysis. But then if it is not ideal, if A0 is finite, and in that case you have to proceed with circuit like this. Okay, so now let's say we have an ideal op-amp, and we said that one of the terminals you connect to the input and another terminal you have to connect using a voltage divider. This is K minus 1 times R and this is R, and this should be connected to this voltage will be V out by K, while this is V out, right? And V out by K is being given here. So if you want to solve this particular scenario, to see what is your gain, it's very simple. We know that op-amp should be connected in negative feedback. Assume that it is connected in negative feedback, and there is a systematic way of figuring out what is negative feedback, whether it's negative feedback or not. It's very straightforward. Assume that you don't know what is the plus and minus signs of the op-amp. Assume that I don't know this, okay, and I have to figure out what is the signs of the op-amp. Then you break the loop at a convenient point. Say for example I have broken the loop here, and then I increase this particular node voltage V out. Okay, if I increase this node voltage V out, this node voltage increases, so this voltage here increases. So if this voltage increases, eventually I want the difference to reduce. Okay, whenever I want I have a negative feedback, because of my action here, some response will be occurring here, and this response should be in such a way that my difference should reduce, okay, between these two terminals. Now this is fixed, so if this increases, and if I want my difference to reduce because of the increase here, I want this to be negative and this to be positive. Okay, so that here the net voltage will reduce. Okay, so I started with something and I am ending up with the negative feedback of the same thing. Okay, and this is what is very important, and going through the loop in this way to establish a negative feedback, I can figure out the signs of the op-amp. And once it is done, I know it is an ideal op-amp. If I know it's an ideal op-amp, then I know that this voltage and this voltage should be same, because ideal op-amp A tends to infinity, that means VD tends to 0. So these two voltages should be same. So V in, this is V out by K and this is V in. So V in is equal to V out by K is I have established, which implies V out by V in is equal to K. It's as simple as that. Okay, and this kind of circuit is called a non-inverting amplifier, which is a voltage control voltage source using op-amp is a non-inverting amplifier. So essentially your input is given to the positive terminal, which will not invert the output, or there won't be any kind of inversion at the output. That's what it means, and it's a non-inverting amplifier. Similarly, if you try to implement what is called current control voltage source, okay, which is very similar. So let's try to do a current control voltage source using op-amp. Let's again assume an ideal op-amp, okay. So assume an ideal op-amp, and then which has 3 terminals like this, okay, and I don't know which one is positive, which one is negative. Let's say we'll figure out using negative feedback, and this is the output terminal, which is something I know, okay. And then current control voltage source, what equation it will have? Output is V out and input is some I in. So to be dimensionally constant, I will have some I in times R1, let's say, okay. I in times R1 is what I have, and it's very similar to that of my current control voltage source using MOSFET. Now that I have an op-amp, that is the only difference, okay. So how do we do it? So we'll do it in a similar way, like this is V out minus I in times R1 is something I have to give it at the input side, another should be compared, okay. So this is V out minus I in times R1 equal to 0. So this is what I want it to be compared. So what I do, I take the V out, okay, and then give some R1 here, and then connect it to this terminal and say that I have an I in supplied here. This is what we did for the MOSFET also, okay. So and then it will have its own RS source resistance, okay, and then connect this to ground, because V out minus I in times R1 is what I want to compare. So the other one should be grounded, okay. This is what I would do if I want to compare V out minus I in times R1. Now you see, this is 0. So if this op-amp is ideal, this voltage also is going to be 0. So this is 0 volt, this is 0 volt, because connected to ground. If this is 0 volt, then what is the current flow through RS? There is no current that is flowing through RS. So this RS, it's like open circuited, it's not there at all, okay. Even though if it is there won't be any current flow here, so it's like open, okay. All the current will flow through R1 only, because none of the current can flow into the input of the op-amp. I is equal to 0 here, I is equal to 0. This we define, because input impedance is infinity, none of the current can flow into the input of the op-amp, and whatever current is there at the output, that will flow here, and then it will come here like this, and go here, and it will flow here, okay. So this I in is something that is flowing through R1, okay, and no current flows in the RS. If you remember in the MOSFET case, while discussing current control voltage source, I asked you to ignore this RS, okay, and the reason is this, because it can, you can always think MOSFET also has a something like a virtual short concept in MOSFET also, but we'll come to that later. So here I hope you understand why this RS is ignored, because it's a virtual short concept. If this is 0 volt, this is 0, and 0 is at here, and 0 volts is here, so no current flows through RS, because it's shorted kind of, okay. It's like this RS is not there at all, that's the idea. If there is no potential difference, there won't be any current flow. So now coming back, I know that this particular, if I consider this particular scenario, or try to write a KVL here, I will say that V out by R1 is equal to KVL at this point, V out by R1, that is current entering this node, equal to current leaving this node, which is I in. So this implies V out is equal to I in times R1. This is what I wanted, and I got it, okay. This is considering this op-amp to be ideal, okay. But remember, I have to figure out the signs of the op-amp for it to be acting in negative feedback. I said that only in negative feedback these two are virtual short, okay, but then I didn't figure out the sign, so I am assuming they are in negative feedback, but how to figure out the sign? Again, you break the loop at a convenient point, you break it at the output, and then this is break here, so you increase this node. If this node voltage increases, this node voltage will increase, okay, and this is at ground already. And if you want the difference, eventually I want the difference to reduce and this point voltage to reduce. That means if this is increasing, if I connect this to positive, then the difference will keep on increasing. So obviously this should be connected to negative and this should be connected to positive, so that the difference will reduce and this value will come down, okay. And that is what I call it as negative feedback, and this is how we figure out the signs of the op-amp. And because the input here is connected to the negative terminal, you call it as an inverting amplifier, which is a current control voltage source. Okay, and of course, as we discussed earlier in the context of MOSFET, this IN and RS can always be replaced with its own Thevenin equivalent. In that case, you will have some VIN and RS like this, instead of this one, and it will go to the negative terminal of the op amp while positive is grounded again, and there will be a feedback, say feedback resistor RF. Okay, and this is V out, and by virtual short, if this op amp is ideal, by virtual short this is 0 volt, this is also 0 volt. So if you write the KVL at this point, you will have current flowing into this node is equal to current flowing out of this node, so which is V in by RS is equal to minus V out by RF. So if I try to find what is V out by V in, okay, I would get minus RF by RS. Okay, so this is also an inverting amplifier, this is also an inverting, this is also an inverting, while this is acting, make it act as a op amp, act as a current control voltage source. Well, this is like old, the Thevenin equivalent of this particular current source and source resistance is given here, and it gets, it is having a gain of minus RF by RS, and it is inverted, and that's why it's an inverting amplifier. Okay, so again the feedback is negative feedback, that is very, very important, and the negative feedback is mandatory to establish the virtual short ideology in case of MOSFETs. Okay, so this is all about building a voltage control voltage source and current control voltage source using op amp.